Learn here, lead anywhere.
Studying about the electronics that is used in IoT device, and we would be studying about FETs, relays and transformers. Field effect transistor is a transistor that uses an electric field to control the shape and hence conductivity of a channel of one type of charge carrier in a semiconductor material. Basically, FET is you might have known about semiconductors, different type of semiconductors. There are NPN and PNP, right? Yeah. So in the same way, FET is there's a PNP FET and NPN FET, and what in FETs we can control the voltage by changing the current. Okay. So that is why FETs can be used as a controlling device. In which, for example, in some devices we might have to give more current, so we would lessen the voltage. If we have to give in the more voltage, we would lessen the current, and vice versa accordingly. Okay, so FETs are unipolar transistors as they involve single carrier trans operation. What is unipolar? Unipolar means there is just single carrier type operation. That means either holes are transforming, means traveling, or electrons are traveling. Okay. Yeah, you have the concepts of the concepts about holes and electrons. So the concept of FET predates by BJT. So basically FET is a like better version of BJT, that is a bipolar junction transistor, though it was not physically implemented until after BJT due to limitation of semiconductor material and relative ease of manufacturing BJTs compared to FET at that time. So basically BJT was the main thing that was previously developed, and we just by some doping and other improvising, we created an FET. Okay, so FET was created. So FETs, so these are some functions. So FETs can be majority charge carrier devices in which current is carried predominantly by majority carriers. So majority carriers can be electrons or majority carriers can be holes. Okay, so in which current is mainly due to flow of minority carriers. Okay, so here we see the current. In some cases it can be predominantly by majority carriers, and in which there is some, like, depending on the current, the voltage can also be changed accordingly, like I already told you. Okay, so the device consists of an active channel. So we have basically active channel that is sandwiched between, let's say we have two channels. It can have walls of N type or P type. Okay, so it can be NPN, where we can have walls of holes or walls of electrons. Okay, so device consists of an active channel. It has a channel or a gateway through which charge carriers, electrons or holes, flow from source to drain. Okay, and the drain terminal conductors are connected to the semiconductor through ohmic contacts. And there is the conductivity of channel is a function of potential applied across the gate and source terminal. Like the third thing, the conductivity of channel is a function of potential. Potential means like the potential difference between the gate and the source terminal. When we vary it, the current is also varied. So this is the basic diagram of the BJT, and through which we can just develop an FET. So in BJT we have C, B and E, that is we have the source, drain and gate terminal, and instead of C, E and B, in FETs we have source, drain and gate. So this is the difference between FET, N-type N-channel FET and P-type P-channel FET. So we have source. What source does? Through which the carriers enter the channel. So the carriers can be either electrons or holes. So conventionally, current entering the channel S is designated by IS. So IS is a designation of the current. Drain, through which the current carriers leave the channel. We have the drain through which the carriers leave the channel after the performing task. Conventionally current, so this is the conventions, that is VDS for the drain voltage, and gate, the terminal that modulates the channel conductivity by applying voltage to G. One can control ID. So we can control ID, how much current is flowing, by changing the conductivity at the gate. So this is the gate over here. Okay, so we can just increase the voltage or decrease the voltage, and accordingly the current can also be decreased. Okay, so these are the uses of FET. So the most commonly used FET is MOSFET, The CMOS or complementary metal oxide semiconductor process technology is the basis for modern digital integrated circuit. This process technology uses an arrangement where usually enhanced mode P-channel MOSFETs and N-channel MOSFETs are connected in series such that when one is off, the another one is on. So FET, so for FETs we have different types. We have MOSFETs and JFETs. Okay. So JFET means junction field effect transistor, and MOSFET means metal oxides, metal oxide field effect transistor. So these are one of the functions, and the common use of FET is an amplifier. Like I already told you, that is a major issue. I mean, that is the major application of an FET. It is used as an amplifier. For example, due to its large input resistance, we have a large input resistance, because if we increase the gate voltage, the resistance can be increased and it can be decreased vice versa. And at low output resistance, so it is effective as a buffer in common drain. So in FETs, electrons can flow in either direction through the channel when operated in a linear mode. Now we have the, like, what are the other applications, like how the FET can be applied in the particular electronics. We can use it as a low noise amplifier, in which, see, let's basically, when we tell noise is basically related to noise in TV channels or in mobile phones, or while you're watching a video or data transfer. So noise is an undesirable disturbance that is superimposed on a useful signal. When we have a useful signal, and basically we don't want noise on our signal, right? So that is why noise is an undesirable disturbance that is imposed on a useful signal. So noise infers with the information contained in the signal. So whatever the information we have in the signal, the noise, it can manipulate the data, it can just create a bad data out of it. So greater the noise, less the information. Okay, so if we have more noise in the data, the information that we get, it can be less. For instance, the noise in the radio receivers develops cracking and hissing, which sometimes completely masks the voice or music. You would have seen the noise in your radios or in your mobile phones when you listen to the songs. If there is noise, there is a particular hissing. You might have observed it, right? Yeah. So that, what does that do? That basically sometimes it just completely destroys the data that we want to transfer. So that is a bad issue in the noise. Similarly, the noise in TV receivers produce small white or black spots on the picture. So you might have observed while you watch TV, and if there is rain or you just pull out the cables, so there are black and white dots on the TV, right? Yeah, that can be an example of noise. So noise may wipe out the picture. Noise is an independent of signal strength, because it exists even when the signal is off. So every electronic device produces a certain amount of noise, but FET is a device which causes very little noise. So this is especially important near the front end of the receivers and other electronic equipment, because the subsequent stages amplify front end noise along with the signal. So if FET is used at the front end, we get less amplified noise at the final output.
Learn here, lead anywhere.